Today we're going to cover implicit differentiation, and all this really is a way for us to find the derivative without solving for y. Okay, and so I have a really basic example here for us to give us kind of an idea of how this might work. Okay, so we're going to start off with this equation y equals minus 3x plus 4, and I just want us to take the derivative. Well, if we want to do that, well, we take the derivative of the negative 3x with respect to x, and that gives us negative 3. And if we were to also take the derivative of this 4, well, the derivative of that constant is just going to be 0. So our derivative here just ends up being negative 3. Well, in a slightly more challenging problem, we have it not solved for y this time. And the question is, well, how do you take the derivative then? Well, we could start by taking the derivative like we normally do. We'll take the derivative of each piece. It's just we have this one weird part here, which we'll talk about in a second. This being it. But overall, right, nothing here looks very surprising. We know that if we were to take the derivative with respect to x of 3x, we'd get 3. We also know if we were to take the derivative with respect to x of a constant, we should get 0. Now the only question is what's going to happen with this derivative with respect to x of y. Well, when we do these implicit derivatives, we're assuming that y is some function of x. Okay. So what I'm trying to say is we may not know exactly what y looks like, but we know that it depends on x. So y might look like, let's say, minus 3x plus 4, because that is what it looks like. And so if we didn't know that this is what y looked like, we could still at the very least say that the derivative of y is the derivative of y. So we'll do that. We'll say plus y prime. And now if you solve this, we get y prime equals minus 3. And we're done. We get the same answer. Well, let's see how this applies to maybe some harder problems. But I do want to just point out this was our explicit differentiation, and this was our implicit. And again, implicit just meant we were taking the derivative with respect to x without having solved for y first. That's all this really means. So here's another one, and let's get started. Let's take the derivative of each piece. And you know what? I'll even pull those constants out maybe for a minute. Pull out the 3, because we know we can do that with our derivatives. Let's do that here too. 5 times d dx of y squared, and then is equal to the derivative with respect to x of 4. Next, let's start trying to evaluate some of these derivatives. You know how to take the derivative with respect to x of x squared. That's just 2x. Okay. And we have 5 times whatever the derivative with respect to x of y squared is. Now, we're going to have to do a little bit more thinking this time on how to take that derivative. So, in the process of doing this, we always assume that y is some function of x. Let's say 3x plus 4. Okay. And maybe let's also say that we were looking at maybe y squared maybe I'll call it f of x is equal to 3x plus 4 squared. So again, the point is that f of x here is just equal to y squared. And I want to know, what's its derivative look like? Well, its derivative, well, we'd use the chain rule. We'd have 2 times 3x plus 4 to the 1, and then times the derivative of the inside. Well, notice here, this 3x plus 4, that was just equal to y. So we have 2 times y to the 1. And then this 3 here is just equivalent to y prime. And actually, I'm not going to put the 1 here so we don't get confused. Okay. Now, as what you can see is to that y squared, we really just took the derivative like usual, and then we noted that, well, y is some function of x, so we should multiply by the derivative of the inside, which is y prime of x. And so that's what we'll do over here. We'll have 2y times either y prime or dy dx. Just depends on how you want to write it. Let's go with dy dx, since that's what the question states. Okay. So again, this was the derivative of y squared, and this was the derivative of the inside. Okay. Chain rule. Okay. Next, we want to differentiate the right-hand side, which is going to be 0. Okay. And now we can work on just solving for dy dx. That's what we're looking for. What's the derivative of y with respect to x? So we have, it looks like 6x plus 10y is equal to, oop, I'm missing something, 10y times dy dx is equal to 0. And let's move the 6x over to the right, divide by 10y, and we'll have our answer. So again, subtracting over the 6x, dividing by 10y, and you can actually even rewrite that a little bit. We could rewrite this as dy dx is equal to minus 3x over 5y, just doing a little bit of simplification. Okay, and there's our answer. One more thing that I'd like to mention before we move on, and that is our implicit derivatives sometimes will have both x's and y's. Okay? And this is okay. It just means if we want to find the derivative at a specific point, we now need to know not just the x value, but also the y value. And we'll get some practice doing that in a later example. But again, I just want to point out, it's actually okay that y is in here. Of course, we wish it wasn't, because it would be more simple if it wasn't. But it's not a problem that it's there. On to part C. And this one here is a little bit more complicated than it looks like. Okay, and the reason for that is this x times y here is actually a product of functions with x's. Okay, remember, y might be equal to, say, 3x plus 4. So when we actually write x times y, well, this is x times something with x's in it, which is something we'd use the product rule for. That means when we take this derivative, we will be thinking about the product rule. So the derivative with respect to x of 12 is just 0. And the derivative with respect to x of x times y is the derivative of the first function, which is x, so that's just 1, times the second function, which is y, plus the first function, which is x, and then times the derivative of the second function. Again, all we know really here is that y is a function of x. So the best that we can say here about the derivative of y is that it is the derivative of y. Okay. And we'll do just like the last one now. Now our goal will be to solve for y prime, and then we'll know what the derivative looks like. So I'm going to go ahead and subtract by y on each side, and then divide by x, and we have our derivative. And one thing that is kind of interesting here is that even though at the moment, again, this has x's and y's in it, well, we actually can solve this equation for y. But I should point out before we move on, we are done with this one. But we could have solved the original equation for y, and if we had done that, we get y equals 12 over x, or how about 12 times x to the minus 1? We could have taken its derivative using the power rule, and we'd end up with what? Minus 12 over x squared. Okay. Now, the question is, well, these don't look the same. Okay. Well, they are. And this is because y, we know, is equal to 12 over x. So if we were to take this thing here and replace our y with a 12 over x, we have minus 12 over x all over x. If you simplify that, that will give you minus 12 over x squared. Okay. So this is a great example to see that both implicit and explicit differentiation give us the exact same result. Okay. Now, we won't always be able to do this. There will actually be equations that we'll start with that we won't be able to solve for y. Okay. And so implicit differentiation will be our only tool. Okay. We won't be able to do explicit differentiation. And we'll just have to accept that we have x's and y's in our derivative.